Hi, thank you for joining our session today. My name is Shivchander Sudaliraj. I'm a principal research scientist at Red Hat AI, and with me is my colleague Wang, a senior principal research scientist also at Red Hat AI. Today we'll be talking about synthetic data generation and data processing, why it matters more now than ever, and how our open source toolkit makes it easier for researchers and practitioners to bring their domain expertise into large language models. So let me give you a quick overview of where we are headed today. First, we'll start with the big question. Why synthetic data? I'll talk about why it's becoming the new scaling lever in AI, not just a stopgap, but the real solution to some of the biggest bottleneck we face currently. Next, we'll dive into SDG-Hub, our open source toolkit for synthetic data generation. This is the hands-on part. We'll go over what it looks like, how it works, how you can start using it right away. And finally, we'll zoom out of the picture to talk about how you can bring your data into your model. How do we take these building blocks provided by SDG-Hub and use them to bring your real domain expertise into these large language models? Because at the end, the value isn't just in the bigger models. It's making them smarter for your work. And then I'll pass the baton to Hao, who will cover data subset selection for efficient training. So one of the biggest conversations happening in AI right now is whether we are literally running out of data. You've probably seen headlines like these. And it's true. When you look at the scale of modern LLMs, the high quality publicly available human data is very finite. We have scraped the web, we've used books, Wikipedia, code repositories, and now we are hitting a ceiling. So the question becomes, if more data is the lever that drives better models, but we can't keep scaling with human data alone, what's next? That's where synthetic data comes in. If you look at enterprises, the picture is even starker. Most of the data that truly drives business values, things like internal documents, transaction records, or proprietary research, they aren't available on public internet. It's locked behind company firewalls. Less than 1% of enterprise data is available in today's proprietary models. And that's rightfully so. If the number goes up any further, that's a problem for the company's security. So to solve the problem, researchers came up with this idea. If we're running out of data, why not just create new ones? And what if we just use LLMs to generate training data for other LLMs? So why are we talking about synthetic now? And why it matters in the current landscape? First, open source models have got incredibly capable. They're now matching or even surpassing closed models in many benchmarks. But strong models need strong data, and that's why synthetic data becomes the fuel. Second, it's now cheaper than faster than ever before to collect and to run inference on these large models, thanks to technology like VLLM. And third, we need diverse and controllable data. Sometimes human expertise alone isn't enough. We need to create edge cases, rare examples, domain-specific data on demand. Synthetic pipelines let us dial in exactly these kinds of examples. And this isn't just a theory or research problem anymore. It's happening currently at every stage of LLM pipeline. Today, you can start with pre-training a language model on completely synthetic data, post-training with synthetic SFT data, and synthetic preference data. And you can even evaluate these models with using LLM as a judge. Over the past 2 years, the research community has exploded with new methods for generating and aligning data for LLMs. This is both exciting and overwhelming. There's a plethora of algorithms, each with its own code base, assumptions, and data format. And that brings us to the real pain point. Which algorithm do I even use? How do I run it? Most of the implementations are ad hoc and fine-tuned for a single data set. How do I adapt it to my domain, my company's documents, my use case, my compliance requirements? Can I build my own pipeline without starting from scratch? These are the kinds of questions we are trying to answer, introducing Synthetic Data Hub. We tried to make it modular and made it intuitive to create your own workflow, and mainly we made it scalable. So let's zoom out and look at an LLM customization workflow. It goes something like this. You start with generating synthetic data, mix it, do some SFT, and then do some couple of rounds of RL, and finally you get a trained model. But if you look at this, the most time-consuming part of this is the synthetic data generation part. And that's what we are trying to solve with SDG-Hub. So now let's talk about SDG-Hub. That's the toolkit we have built to make synthetic data generation simpler, modular, and scalable. So what is it? SDG-Hub lets you build synthetic data pipelines like Legos. You can mix and match LLM-powered and traditional blocks to create exactly the pipeline you need. You can compose and orchestrate flows in YAML from single, simple blocks to complex multi-stage pipeline. And you also have the abilities to auto-discover. It's schema-aware, so you instantly knows which flows are available. You can validate your input and get the correct dataset formats without doing any guesswork. So why does it matter? Instead of stitching together one-off scripts, SDG-Hub gives you a reusable framework with consistency and repeatability built in. It's designed to scale synthetic data generation. We are completely async native with built-in monitoring, so you can process at production scale. And now it's easy to extend and customize. You can create your own blocks or plug in your own logic into the existing flow without minimal code. So let's go over SDG-Hub's core fundamentals. At the heart of SDG-Hub are something we call blocks. These are abstractions, and they're the building units of everything you do with this particular toolkit. First, blocks are self-contained and reusable units. Each one transforms the data in a specific way. For example, an LLM block might generate an answer, while another one parses the answer and turns it into a structured JSON. Secondly, they all share a consistent interface. So no matter what the block does, it always takes an input data, applies some generate or processing, and then produces the output data. This makes it easier to swap in and swap out, or even chain blocks without worrying about mismatch code. Third, these blocks are composable. Just like Lego pieces, you can stack them together to build powerful data generation pipelines. Next, if blocks are the building units, flows are like the orchestration layer that connects them into complete data generation pipeline. First, flows let you chain multiple blocks. So you can consecutively chain LLMs, transformations, and evaluation into a sophisticated pipeline. Instead of running one block at a time manually, you define the whole workflow once and run it end to end. Second, these flows have a flexible definition. You can build them Pythonically or in a YAML. YAML gives you a clean, decorative way to define these complex workflows with metadata, validation, and model recommendations built right in. Third, these flows are built for optimized execution. You can dry run a pipeline to validate it, run it step by step for debugging, or execute it asynchronously with built-in parallelism. On the right, you will see a sample YAML flow. In this, you see the multiple blocks defined in a sequential manner. So what the flow does is run them one by one. So everything we have seen so far, the blocks, the flows, the quick start, it comes out of the box. But what if you need to create something unique to your domain? With SDG-Hub, the process is simple. First, you explore the existing blocks. Before you reinvent the wheel, just browse the built-in library to see what's already available. Most common data generation transformation and evaluation tasks are already implemented. Next, you can fill in the gaps with these custom blocks. If you can't find what you need, you can extend SDG-Hub by writing your own block. Then, you can wrap them as a flow. Once you've got your blocks, you can define a flow in Python or YAML and chain them together. And then finally, you can generate. You can run your new pipeline with the same generate call you saw in the quick starts. Right, now that we have primed with the toolkit, let's look at a practical use case. How can we use SDG-Hub to customize a language model for domain expertise? So let's take this example. Let's say I want to create a finance bot for IBM. We have on the left, we have IBM's financial documents. This is quarterly report. Now, I want a bot which can answer a particular question like this. Name two business lines that showed year-over-year growth, but turned negative at constant currency in Q2 of 2025, and report both the percentage changes. Now, if I give this document to a model and I want to answer this question, there are two main problems. First, the model simply doesn't have the knowledge. It doesn't know IBM's quarterly earnings, especially for 2025, which was quite recent. And this is because models only get updated on a particular time period. So it could be every 6 months or a year. So until it's captured by that particular cycle, the model will simply not have the knowledge. So RAG comes to our rescue here. So you can simply feed in these documents in a RAG set. But even with that, if you use a retriever, the retriever may miss or misalign the context to answer this question. For a multi-step query like this, it might fail to combine the right pieces of information to produce a correct and coherent answer. I'm looking for an answer something like this. So how do we train a model to get this? That's what we're going to be looking at. How to go from raw documents to a domain-tuned model. You start with processing the documents. Then you generate synthetic data on those documents. And then you can post-process and train a model on that. So let's break this down step by step. Let's start with processing the documents. Enterprise data usually lives in PDFs, Word docs, or scanned reports. These formats are not really LLM friendly. To make them usable, we're going to use a tool called docling. Docling takes your raw documents and converts them into structured markdown, which is clean and a consistent format that LLMs can easily consume. It's as simple as simply installing docling with pip and running a single command to suddenly turn your enterprise reports like these IBM financial statements and get them converted to a format which is ready for synthetic data generation pipelines consumption. So once the documents are processed, the next step is to actually generate the synthetic data. This is where SDG-Hub comes in. And the workflow is really simple. First, you discover the available flows. These are pre-built-in pipelines for common data generation tasks. We already have pipelines set up for generating data from these ground documents. Next, you can configure your teacher model. This could be an open source model like Llama, or you can have a hosted model like GPT. Finally, you simply call the generate function on this dataset. Behind the scenes, SDG-Hub orchestrates the pipeline, prompts the teacher model, structures the output, and produces clean, training-ready data. So now we have walked through the full journey of starting with raw documents, processing them into an LLM-friendly format, and generating these synthetic Q&A. This shows how we can turn unstructured enterprise report into domain-specific training data for customizing these models. And with that, the natural next question becomes, how do we efficiently select the best subset for training? That's where Hao will take over and walk you through the data selection process.
Thank you, Shiv, for the presentation on the SDG-Hub. My name is Hao, and next I'm going to talk about data subset selection for efficient large language model training. So many results I'm going to present next are from our collaboration with Krishna, who is a research scientist at the IBM Research. So many thanks to Krishna. When using a large language model, there are 3 domains for reducing computational cost: data, training, and inference. So in today's talk, I'm going to focus on the first part, how to optimize for data efficiency. And specifically, I'm going to talk about how can we choose a subset of training data that is most efficient and scalable to your own domain. So as shown in these 2 figures, the size or the parameter counts in your large language model, as well as the number of available training data, have been increasing in recent years. So this creates 2 new challenges. First, in order to either pre-train or fine-tune such big size large language model, you need more and more compute power. And second, pre-training and fine-tuning dataset have been extremely large, and they are also very inefficient for us to train large language model directly on them. And more specifically, regarding the second challenge, existing large language model training data are mostly coming from internet, which have a lot of redundancy. So it is crucial to identify such redundancy and create a more efficient way for mitigating data redundancy before we start training your large language model using such data. And that leads to today's topic, data subset selection. There are 3 use cases that can motivate why we care about data subset selection. The first use case is that can make your training recipe more efficient. And more specifically, if you can use only 10% of your training data for training your large language model, that can roughly lead to a factor of 10 much faster training times. And as a result, you save a lot of compute power. So the hope for the first use case is, again, reduce the number of training data while still maintaining the same performance after you train your large language model using such data subset. Second, data subset selection can help you customize any general purpose large language model to be a domain expert. And more specifically, you can choose the subset of data that are mostly relevant to your domain or to the task that you are interested in, and use such a subset to fine-tune the large language model to make it tailored to any deployment environment you care the most. The third use case is to choose data subset that is complementary to existing training data. This can help add new novel information when continue training your large language model. And this involves identifying data subset that can fill in knowledge gaps or introduce new examples that not yet represented in the model's training data before. It can also be used to exclude data that may contain either bias or harmful information. So far, we have talked about why we care about data subset selection, and also 3 use cases of data subset selection. So next, I'm going to talk about how we conduct data subset selection, what the real algorithm looks like. So the main secret recipe here is to formalize this data subset selection problem as a mathematical problem, which is to optimize a set function given some constraint. So here, the objective function is a utility function that we aim to maximize. The variable here, which is S, is the index set of which data points from your training data we want to select. However, solving this problem in general is NP hard, because this is a complementary optimization problem. So the main technical contribution here is to choose the objective function from a very special class of functions, which is called submodular function. And researchers have already proved that if you optimize submodular function using greedy algorithm, you can get an approximately optimal solution with theoretical guarantee. And that's what we leverage in this practical algorithm. So more specifically, again, this is the mathematical formulation we use for our algorithm. Again, given a training data, so we want to maximize the objective function z here over the variable s, which is the index set of the selected training data. So here, the constraint says you only want to choose capital K number of data from your big training data sets. So more specifically, this is how we solve this optimization. So for each training data point, we apply an embedding function to map this training data point to an embedding space. After that, we compute pairwise similarity between each pair of training data in the embedding space. Then, as I mentioned, we optimize a submodular function as our utility function to find the optimal data subset. And this is done by using a very special submodular function called facilitated allocation. And intuitively speaking, so by optimizing this submodular function, you can find a representative subset of your training data that can represent each one of your training data. So this is a quick result we ran last year when we applied this submodular function optimization for data subset selection using InstructLab. And as you can see, here we only choose 50% data subset. And then we use such data to run InstructLab training. And on two phases, both on MLU evaluation and on MT bench evaluation, we can roughly maintain the same level of accuracy. Well, we can achieve a factor of 2 speed up in training time. So in quick summary, this is the general pipeline we do for data subset selection and in general, how we apply this algorithm to the training pipeline. So we start with preparing data according to what Shiv described in the first part of the presentation using the SDG-Hub. After we generate synthetic data from the SDG-Hub, we run this data subset selection to choose the most relevant and representative subset. We use them to train the model and then test the fine-tuned model using existing benchmarks. And this is a visualization of what I described. Specifically, we run the SDG-Hub to generate instruction tuning data from different domains. We map each one of the data points to an embedding space using an embedding function. Then we run this data subset selection algorithm by optimizing the submodular function I mentioned before, and that can give you a subset of data. After that, we divide such subset of training data into different domains. And from each domain, we sample training data, use that to train any open source large language model using our training recipe. After fine-tuning our model, we evaluate the fine-tuned model on existing benchmarks. And that's all we have today. Thank you so much for attending today's presentation.